Hello everyone, I'm Miranda and I'm super excited to be here today to present the work I did this past summer with Lindsay Smythe at the San Andres National Wildlife Refuge. During a 12-week internship, I helped analyze bighorn data that was collected over the past few years. For my first talk, this one, I'll be presenting a population model that I developed to help understand population dynamics of the bighorn within this region. And I hope you stick around for my second talk following this one, where I will be discussing habitat use and resource selection by these bighorn. I'll get us started with a bit of background about the San Andres National Wildlife Refuge. This refuge was established in 1941 to help conserve and protect the bighorn in the San Andres mountain range near Las Cruces, New Mexico. The range spans the southern portion of the San Andres Mountains and is completely surrounded by the White Sands Missile Range. This refuge serves as crucial bighorn habitat as it is the largest intact area of the Chihuahuan Desert in the U.S. Since the establishment of the refuge, the bighorn population in this region has fluctuated greatly. In 1941, when it was established, there was thought to be about 33 bighorn in the region, and the population number steadily increased to the late 1940s. However, a severe drought in the early 1950s led to increased competition between the desert bighorn and livestock for limited forage, and the population began to decline. Also, during this time, from the early 1940s to the late 1960s, extensive predator control was conducted in the region, which may have aided the persistence in the population during that time. Likewise, in 1951, the White Sands Missile Range was established around the refuge, which eliminated interactions between bighorn and domestic sheep in the region, thereby limiting competition and the spread of disease. So we saw the population really increase after that time. However, despite no contact with livestock in the late 1970s, a scabies outbreak decimated the herd. And the upper picture here shows a ram with mites in its ear and some lesions. And this was huge news. It even spread to the New York Times, where they reported that 3/4 of the desert bighorn sheep within this region had been decimated by this disease. And the herd continued to dwindle until only one ewe remained in 1997. And this is not actually a picture of her, but I imagine she looked pretty similar to this. This looks like a pretty beautiful ewe. And this ewe was actually able to have 2 more lambs before she died. So there is some genetic consistency within the population. And in 1999, after no signs of scabies remained, biologists started to re-release bighorn sheep back into the refuge, and by 2005, they had released 57 total. And these sheep came from the Red Rock Wildlife Area and the Kofa National Wildlife Refuge. And since then, the population is believed to be steadily increasing. And in late 2017, early 2018, the New Mexico Department of Game and Fish partnered with the U.S. Fish and Wildlife Service to collar some of these bighorn. So they captured and collared 13 bighorn, 10 ewes, and 3 lambs. And this was to get a better idea of where these sheep were on the landscape to inform aerial surveys. However, these collars have also provided other useful data that we hope may allow us to better understand population dynamics in the region. So the goal of my project was to model San Andres bighorn population dynamics based on aerial survey estimates collected from 2015 to 2019 and based on the collar data that they've collected over the past couple of years. To do this, I constructed a stage-based post-birth pulse matrix model for female bighorn using 3 life history stages: lambs, yearlings, and adults, or ewes. And our model was pretty similar to the model used by Heather Johnson to model population dynamics of the endangered Sierra Nevada bighorn. And others, like Esther Rubin, have used more complex matrices that break up the adult life stage into multiple age classes with different reproductive capacities and survival rates. Although these complex models certainly offer a more precise tool for understanding population growth and persistence, many of these age classes are difficult to distinguish during aerial surveys and therefore may not be particularly useful to managers attempting to understand bighorn population dynamics. Our hope was that this simplified model would offer a more realistic alternative for managers hoping to estimate future populations. And we were able to determine these different vital rates. So we have here the probability of lamb survival, the probability of yearling survival, the probability of adult survival, and then the percent of ewe recruiting a female lamb, We were able to estimate all of those vital rates using data collected either from aerial surveys or based on the collar data. We estimated the vital rates from our population using methods adapted from others, specifically Esther Rubin's paper from 2002. To calculate or to estimate lamb survival, we compared the lamb to ewe ratio from one year to the following year's yearling to ewe ratio. And we used data from 2015 to 2017 because that was the only recent years where there were consecutive counts. And I should note that when we calculated this yearling to ewe ratio, I included yearling ewes from the survey data as well as C1 rams. So this could be an overestimate of lamb survival, but unfortunately that's just the best that we have, the best data that we have. And using this method, it did nicely match the estimate of lamb survival used in Rubin's population model, which was 50%, and here we had a survival value of 47%, which is quite similar. So I think that although this could be a generous estimate of survival, it seems like it matches what others have found. And I'm going to explain a little bit later how I've modeled sort of different levels of survival, and we can see what effects that has on the population. We also used the assumption that Rubin used in her 2002 paper. We assumed that yearling survival would be about 10% lower than adult survival. So here we have our yearling survival at about 80%. And then to estimate adult survival, we used the average ewe survival based on collared ewe mortality events from 2019 and 2020. So in 2019, 2 of the collared ewes died based from predator attacks, likely mountain lion, and in 2020 we didn't have any of the collared ewes die, so that gives us a 80% survival rate in 2019 and a 100% survival rate in 2020. So we averaged the 2 of those to give us a 90% survival rate for adults. We were also interested in determining how changes in reproduction could influence this population. So we modeled reproduction under 2 different scenarios. And in this case, we're looking at the percent of ewes that have a female lamb. So under our low reproduction scenario, we're estimating that about 12% of females have a female lamb, and that estimate was based on the estimates used in the Rubin paper, and that is modeling a declining population. And then we also wanted to estimate it at maybe a more stable reproductive scenario. So we used this high reproduction scenario, which is based on the idea that 100% of ewes are pregnant each year, and 50% of those would have a female rather than a male lamb. And these high reproduction scenarios are based on some data that others have collected in Overstreet and in Kane. They both found that 100% of the ewes that they surveyed were pregnant. So this may be a little bit high, but it does seem to happen in some of these populations at least. And during 2019 aerial surveys, they observed 21 lambs, 3 yearling ewes, and 71 adult ewes. And in our model, we divided this lamb number by 2 to represent only those lambs that were female. And we used these stage abundance estimates to determine stage abundance and population size for the next 10 years based on those reproductive scenarios I gave previously. And we also calculated the finite rate of increase at a stable stage distribution for 2,000 replicate matrices. And these matrices were created by randomly selecting vital rates from a beta distribution that was created using the mean and standard deviation of each of the rates. So to jump right into kind of what we found with our results, the population growth does depend on the reproductive capacity of the ewes. So in this figure here, we're showing the year on the x-axis, and we're starting at 2019, which is where we observed those initial estimates, and we're projecting that into the future 10 years to 2029. And each of these lines demonstrates the different stage abundances for each of our 3 stages, and we see that by 2019, we do see this sort of dramatic decline in the number of ewes that we would see in our population. Now this is at that low reproductive scenario, where only about 12% of ewes have female lambs. Now, when we increase that reproductive capacity to 50%, we do see that ewe number increase. This indicates that we have a growing population. And indeed, we do see an increase in the population size at that high reproduction scenario. So what this is showing is combining all the abundances of the different stages and projecting that again into the future 10 years. So at that high reproductive scenario, we see an increase in the population, and the low reproductive scenario, we see a decline in the population. Now, this isn't surprising, but it is sort of reassuring that, we probably fall somewhere here slightly below what that high reproductive capacity is. So we should still expect our population to increase. And when we look at our lambda values, we see that under that high reproductive scenario, we're expecting to see our population increase by about 5% each year, which is good news. And again, with that low reproductive scenario, we would expect to see our population decline by about 5% each year. So we have quite a bit of range here between that low and high, but our actual value for percent reproducing is probably going to keep us right up here above that vital 1 where we have a stable population. And like many others have shown, when we ran an elasticity analysis, which shows the relative contribution of each individual stage or each individual vital rate to population growth, we do see that adult ewe survival is the most important stage in predicting whether or not this population will stabilize, decline, or increase. And to show this visually, I changed the vital rates in our model by increasing the survival of each of the different stages by 5% while keeping the other stage vital rates exactly the same. And what we see here is, when all of the stages are as we initially had it in our model, so this would be that none that you see on the x-axis, we see that 5% increase in population. If we increase either lamb or yearling survival by 5%, we do see a slight increase in population size, but those increases are exactly the same regardless of if we increase ewe or lamb survival. However, if we increase ewe survival by 5%, we see a dramatic increase in lambda, which would suggest that the population would then be increasing by about 9%. And we can see this here again, that reductions in ewe survival could lead to population decline. So our model was showing a 90% average survival rate for these ewes. And we can see that if that survival rate declines, we might expect that population to decline as well. So at its 85% survival rate, we see that the population is nearly stabilizing, so almost at that 1 lambda value. And when the vital rate for lamb survival decreases to 80%, we see that that population would also decline over time. So this is really important because, in our model, we averaged that the survival being 90% between 2019 and 2020. However, we did see an 80% survival rate in 2019 with our collared ewes. So it really does suggest that we may have some issues in the future if we're not able to keep that survival rate high among the ewes. But maybe some good news is that reductions in lamb survival have really little impact on population growth. So, we used that value of 47%, which, as I suggested earlier, was probably a little bit high. But even if we reduced lamb survival by 20%, we would still see an increasing population. That is, if we manage to maintain high ewe survival. And I'll end this with some brief conclusions, but this is, of course, preliminary. And if you all have anything that you might have as suggestions or additions to this model, we would greatly appreciate those. We're hoping to develop this a little bit further into the future. But based on these crude estimates of vital rates, the San Andres Bighorn population does appear to be stable, and this suggests that the reintroduction efforts that occurred over the last 20 years really do seem to be successful. And this simplified matrix model seems to pretty accurately estimate population parameters, though more intense monitoring is needed to see how this model could compare to others that have more fine-tuned age-specific reproduction and mortality rates. And given that this population model demonstrates that survival of the ewes does play the largest role in population stability, future monitoring efforts and augmentation or removal efforts should focus on those ewes. And with that, I'll take any questions, comments, or suggestions. And I just want to say big thank you to Lindsay for all her support in this, the New Mexico Game and Fish for sharing their telemetry data and supporting this presentation, Kathy Longshore for all of her advice and suggestions, and the U.S. Fish and Wildlife DFP program that made this internship possible for me. And I'll end here with our contact information.